everybody. Welcome to week 6 of PhD Live because I skipped weeks 4 and 5. I didn't do that on purpose, but it's been a busy few weeks. So I have some updates. I think the best way to sum up what I've done for the past few weeks has been, now that I'm settled into sort of the regular routine of the PhD, sort of figuring out what extra things I can do, what I have time for, and what kind of the most valuable extracurriculars to pack in to my schedule are. And I think it's turning out to sort of be 3 main categories. The first one is definitely conferences and meetings that I've been able to find nearby, usually free of charge and registered for, and these have definitely been interesting kind of excursions to add on to the stuff that I'm studying on a day-to-day basis. So 2 weeks ago I went to it was kind of a unique conference. It was a memorial conference for Sir Michael Atiyah, who, if you're at all into math, you'll know about him. He was arguably the most significant mathematician of the last century. Passed away last year, and really made some landmark contributions all across. I mean, I'm not an expert, but definitely a lot of different areas of mathematics. And I think one of the cool things about him is that even though he was not a physicist and never really claimed to be a physicist, he made a lot of contributions by collaborating with physicists. So I think he's a good role model for working with people in fields that you're not necessarily an expert in, but if what you are an expert in relates to something, then that's a good enough reason to find someone who you can work with, and together you can produce something meaningful. And so the cool thing about this conference, which I'm pulling up the description of on the side here, was that the speakers were all people who he had collaborated with over the last couple of decades. I mean, and there are probably dozens and dozens, if not hundreds, of such people. But the 5 who spoke are all physicists, and all had some really interesting perspectives on how his work intertwined with their own, and how the results that he discovered, especially in geometry over the course of his life, are still continuing to impact new physics. Really cutting edge models of both the really large scale, like gravitational physics, and also tiny scale quantum quantum groups, like in terms of what am I trying to say? Like quantum computing, sort of structures where you're trying to manipulate quantum states for some sort of technology purpose, and then also like fundamental quantum mechanics, so particles and what else, like string theory to some extent. But the point is, the stuff he did is really has really spread all across the board. So that was a really cool conference to attend. And then for an added bonus, they offered, which I didn't really know what it meant ahead of time, that this meeting is on the Friday before the memorial service for Sir Michael at Trinity College Chapel. And when I signed up for this, I read it kind of quickly, and just kind of in my mind that was, oh, it's a memorial service. He passed away. That'll be, a nice way for the people at the conference to remember him. And what I didn't really expect was that this wasn't just a memorial service. This was the memorial service for Sir Michael Atiyah. I definitely felt a little out of place there, surrounded by people who had known him for, in many cases, much, his entire life. Like his whole family was there, and they did this really incredible service to remember him. So that was pretty breathtaking. I don't think I will forget that anytime soon. And it's a good lesson in going to conferences, even if you don't know exactly what's going on, because you can get some really memorable experiences. And it's definitely inspired me, which I'll talk about in a little bit, to spend some more time on pure math, because I haven't done so much math in a while, but I like the idea of following his example of doing both a lot of math and a lot of physics. Let's see. Oh, Logan says, "Oh, that's nice of you, Logan. Thank you." And then let's see. Moving on. Last week, much more relevant to my research, but also interesting in just different ways. I went to the APEC community meeting on neutrino double beta decay, which is, as I understand it, an international, European focused, but very very transnational body that discusses this specific problem of resolving whether double beta decay can occur without producing neutrinos. Trying to investigate this process, and if we can measure it, it may or may not even be possible. If it is possible, which depends on certain properties that neutrinos may or may not have, then measuring the rate at which it happens can give us some really, really precise information on the neutrino mass spectrum, and I think also potential charge parity violation properties of neutrinos. So there's a lot of stuff to be gained here. And this conference was interesting because it was mostly experimentalists, which I am not. But yeah, looking back at the timetable, most of this was just a single day thing, but representatives from all of the major upcoming, proposed, but likely most, if not all of these, will go ahead experiments that are trying to study neutrinoless double beta decay in Europe. And they all have pretty different designs, pretty different motivations for what they're trying to study. It was pretty interesting to see them all kind of up there making their case, but also interacting with each other, challenging each other's assumptions and experimental designs. And it was definitely a really productive environment, even if I probably was optimistically understanding like half of what was going on. It was really that half was pretty cool stuff. Definitely one of the funniest things that happened was these experiments are competing for funding from, I think in many cases, some of the same funding bodies, which doesn't mean they can't both get funded necessarily, if they make a good enough case. But I think often that does happen if you have a lot of experiments that are trying to sort of achieve a similar goal, that whoever is providing this money, whether it's a government or a private organization, would probably hedge their sometimes they might hedge their bets, I guess, by funding more than one. But if one of them is very convincing, then I could see them just funding that one and not the others. But someone pointed out that I think it was someone from one of these experiments, even if we do all get funded, even if all of our experiments get to go ahead sometime in the next 5 or 10 years, there's not enough caves in Europe to fit all the experiments, because all the one thing they all have in common is they require underground space to put these detectors where you're shielded from neutrinos that are just background noise, or closer to the surface of the Earth. So you want these underground. So not enough caves, which is, I think, a pretty unique problem to have. I can't think of any other field where you suffer from the not enough caves obstacle. But it's a real problem, because even if not all of them get funded, there's other types of research beyond neutrinoless double beta decay that need underground space for one reason or another. And excavation is an expensive thing that maybe one experiment or another doesn't actually factor into their budget, because they're kind of assuming we won't have to excavate the cave space. We'll just someone will let us use some cave space. But I digress. I thought that was a pretty interesting phenomenon. So conferences has been definitely one category. The other development is that I managed to get myself elected, which I'm pretty excited about, as the PostGrad Student Rep from my faculty. So that's the School of Math and Physical Sciences at UCL. I sit on this board of sort of student advisors who represent the needs of the students and also help advise the university on policy decisions that impact students, especially in terms of like student welfare, education, research. All these things, impact me personally, but it's nice to know that I have a chance of doing some real on the ground work and helping other students while I'm here. And I also just found out today that sort of as an added layer to that, I'll be the representative for all postgrads to the research, the school like research decision making committee. So that will be, I think that'll be a pretty interesting responsibility to have. Like a fun, it should be a fun thing, but also an important thing. And I think it'll drive me to understand a little bit better at the, rather than just the individual professor or research group level, but at the department and then university level, how these funding decisions get made, how research strategy gets decided, and then how those effects trickle down and impact students in the end. So I'm looking forward to that. And then number 3 on my new extracurriculars list is just learning lots of math. I can't emphasize enough how much I love math just across the board. So I think I'm realizing now that the specific type of research I'm doing at the moment doesn't require much math beyond what I already know. There's some sort of technicalities that I need to understand better about how the standard model of particle physics works, how these different neutrino mass mechanisms work, but those are machinery, mathematical machinery built upon foundations which I do know, and that leaves me with sort of a void, I think, where I'd like to put some time, as I've kind of always tried to do with building some new foundations while I'm at it, even if they're not going to be useful to me right now. There's a lot of them to learn, so I might as well get ahead for when I do need them. So one of them, definitely directly inspired by the Michael Atiyeh conference, is projective geometry. So understanding better these sorts of exotic geometric spaces where, as I understand it, a lot of kind of interesting new fundamental theories get constructed and live in projective geometric spaces rather than the standard ones that we're comfortable with. I don't know kind of what that means yet, but it's on my list, and I've started a couple small textbooks. We'll see how that goes. And then the other category, which I guess sort of indirectly came out of this conference as well, with the discussion of like braiding quantum states and quantum computation, is quantum group theory, which I tried to learn a while ago, and I realized at the time that I didn't have enough like algebra exposure, like abstract algebra exposure, to kind of understand the basics of it. But I think I do now, or at least I sort of have a better strategy for learning these sorts of math things. So I'm going to work on that too. And at some point, I guess I'm just sort of prefacing, at some point I'll do a stream about each of these topics once I have enough material to talk about. So that's pretty much the other things update. Onto the actual research. So I think where I left things 3 weeks ago, I was trying very hard to, where is my code? It's here somewhere. Well, this paper is useful. I was getting some code running using the Markov chain, the Monte Carlo Markov chain framework of sampling a complicated probability distribution, which in this case is one that is specific to this neutrinoless double beta decay question. So we have this parameter space for neutrinos. And when by parameter space, I mean the set of variables that describe neutrinos. Now that we know they're massive, there's a bunch of numbers that need to be measured. So you got the neutrino masses, 3 of them, and sometimes that's represented as the 3 masses, and sometimes it's represented as these. I should probably zoom in on this paper a little bit so you can actually see it. Yeah, so sometimes it's represented as these squared sums, squared differences between the masses. And the reason for that is that in oscillation experiments where they look at the neutrinos coming from the sun, coming from the atmosphere, letting them travel over some long distance, and I guess we also do on-the-ground experiments. They're called long baseline experiments, where you make some neutrinos in a beam and then let them travel for hundreds of kilometers and then measure what the ratio of the 3 types are at the other end. These oscillation experiments only allow you to measure these squared mass differences. They don't let you measure the actual masses. So we have pretty good numbers on these 2 things, but we only know the sign of this one. So we know that the mass of the second neutrino state is greater than the mass of the first state, which is represented here in this diagram. But we don't know whether the third state is bigger than both of those or a lot less than both of those. This first one's called normal ordering because these 3 states roughly, but not at all exactly, correspond to, or I think at one point they were sort of thought to correspond to 1 to the electron, 1 to the muon, 1 to the tau particle. It turns out that because neutrinos are massive because they mix with each other, that those 3, they're called the flavor states, the 3 flavor types of neutrinos, are not really the same as the 3 massive types of neutrinos. They, like one of these 3, each of these 3 is some combination of the other 3, and that's represented with the colors here. So the massive neutrino number 1 is mostly blue, mostly an electron neutrino, but it has a little bit of the others. Number 2 is mostly mixed. It seems like it may even be kind of equally all 3. And then number 3 is a pretty big mix of muon and tau, but very little electron. So these are sort of the 3 massive flavors of neutrinos, is what I'll say. Based on, because these do still follow this kind of natural progression of going from traditionally lighter flavors, because the electron is lighter than the muon, is lighter than the tau particle, going from lighter to heavier flavors, you expect the neutrinos themselves to go from lighter to heavier. We just don't know for sure if that's the case. So if it is, it's called normal ordering. Otherwise, it's called inverse ordering. I believe the latest experiments have ruled out inverse ordering to a statistical accuracy of like 3 sigma. So if you're treating it statistically as like a normal distribution, like a Gaussian, then the odds that it's the inverse ordering are 3 standard deviations away, which is something like 0.2%. Pretty small, but not 0. We just don't we don't know yet until we have more information. And things in particle physics have gotten to that point before and then turned out to actually be right. So it's definitely not out of the question. But so the question is, in either of these cases, we'd like to know what the actual masses of the neutrinos are rather than just these differences between them. So finding that absolute neutrino scale is hard. The other thing that we can do is from cosmology, from the fluctuations in the cosmic microwave background, where there is this layer of neutrinos that comes from there and is detectable in the way that it influences the non-uniformities, I guess, in other signals. Don't understand how that works very well, but somehow you look at that data and you can get a limit on the sum of the neutrino masses, not on the individuals. But this is still a pretty useful quantity to have because it it doesn't really tell you anything about the smallest neutrino mass, but I guess it sets a scale for what the largest ones could be. The lightest one could be 0. We don't know. It is possible still for there to be one massless neutrino and the other two massive. But by limiting the sum, at least we find out more about what the large ones are like. So that eventually leads to these two plots, which are an idea of given the lightest neutrino mass, if we knew what that was, what would the mass that's associated with the neutrinoless double beta decay transition, so the resonance energy at which, when you normally have double beta decay, you produce these two antineutrinos. In neutrinoless double beta decay, those annihilate with each other, which is only allowed if the neutrino is its own antiparticle. If that happens, it happens with a specific energy, which we treat as an effective mass for the double beta neutrinos. And that is kind of what is probed, because that mass determines the likelihood that decay will occur at all, if it can occur. So once we can measure the likelihood of that decay, the lifetime, you could say, of nuclei under neutrinoless double beta decay, forgetting about regular double beta decay, which is so many orders of magnitude more likely, it's not even funny. Seriously, like the lifetime, I don't know, the half-life of something radioactive could be anything on the order of seconds, for something really radioactive, to hours, days, years. These are the scales nuclear physicists are used to working with for radioactive things. Then you have not very radioactive things that are more like centuries or thousands of years. We know for sure, just based on the most recent neutrinoless double beta decay experiments, different experiments have given different numbers, but roughly we know that the lifetime of, I should find the number so I'm not just quoting nonsense, but yeah, where is that? Yeah, here we go. Lifetime of 10 to the 26 years. So, like, for scale, the universe is like 10, I think it's 10 trillion years old. That sounds right to me. 10 to the 13. So, like, as many years as there are in the lifetime of the universe, that many lifetimes of the universe. That's how long we're talking about for the half-life of something under this decay. It's ridiculously long. That's why we have to get, in order to study this at all, you have to let neutrinos generate a huge amount of potential decays in a big detector and hope to observe just a handful or one even. That's the kind of scale of the problem here. But so knowing the relationship between these two quantities, which we would like to find out both of them, but we can't measure the latest neutrino directly. So measuring M beta beta can give us some information. These two bands are, whether it's red if it's normal ordered and blue if it's inverse ordered. So most likely we're down in the red band, which is unfortunate because as you go down in mass, that's harder and harder to measure. That corresponds to longer decay lifetimes. It becomes less likely. And the next, these purple bands are the experiments that have been done recently. The upcoming ones that I learned about at that conference mostly have the potential to push down to about 10 to the minus 2 here. So they should at least be able to, if it's in the inverse band, then great, we'll discover it. We'll measure, we'll see neutrinoless double beta decay and we'll know that. Or we'll rule out the inverse band. And there's some chance that that the lightest neutrino mass is quite heavy and it's up in this range. That would be good too. But if we don't see it, there's still a lot to be ruled out, and it'll take a whole nother generation or two of experiments before we can get down and explore this whole parameter space. The other plot that gets thrown around a lot, rather than plotting on the horizontal axis here against the lightest neutrino, you can plot against the sum of the neutrino masses, which gives a better idea of how good is this cosmology limit. So the Planck survey of the cosmic microwave background did this horizontal band from the right, and this is ruling out a whole bunch of space of both the normal ordering and the inverse ordering, and I'm not too up to date on if there's some better survey of planned, but once again, we'll either discover inverse ordering or rule it out before we can totally know for sure about normal ordering, if it's in the normal ordering area. So that's, I'm just giving that background because these are basically the plots I've been trying to reproduce. So I'm not doing any new science yet. I'm just trying to replicate what has been done, which is being able to statistically look at first the physics, the relationship between the base variables here, which are essentially the three neutrino masses, and then some phases that talk about the mixing between there's two phases, which are the mixings between the different mass states, and then if neutrinos are their own antiparticles, there's some phases that sort of qualitatively describe how much can they annihilate with themselves. I think that's a correct way to put it. There's more parameters that have to be factored in, and that's why these blue and red bands have this width. If we knew those phases, then these bands would just be straight lines. There'd be a direct relationship between the lightest mass and beta beta, but we don't know them, so there's this range, and I don't think there's any likely way of directly measuring those, other than to understand better what's going on in this plot and possibly constrain them. So the idea of the physics here is, I know what all those variables are. I know, according to the latest neutrino sort of accepted neutrino theories, how they relate to these observables like m beta beta and the sum of the neutrino masses, and then I can sample across that distribution, but I want to also sample applying these different experimental results. So saying we know that from this Hamland-Zen experiment that with 90% confidence the m beta beta value is less than whatever this number is, 2 times 0.2 EV, and that's just this isn't giving us the whole distribution. This is just giving us a single confidence level, but there's some drop off there above which it becomes very unlikely for the neutrino m beta beta mass to be above that. So plugging in the shapes of those constraining distributions and then seeing what the sampling looks like after that, and not just with one experiment, but with many of them, because all of these experiments combined together are stronger than just one. So onto the code, where we can judge for ourselves if I did that at all right. I have written a good amount of code over the last couple weeks, so I'm pretty proud of that. Yeah, so this is sort of the main structure I've got going right now. I think last time I showed off my Markov Chain Monte Carlo library. Yeah, that's right. And I was using it, at the time I was just using it to try to produce points in like a circle, in like a circular ring distribution as sort of a test. It didn't really take that much longer after that. It might have even been the evening after that stream when I got that working. it's taken a lot longer to be able to apply it to the physics, because you're talking about just a more complicated example, and I needed the ability to plot, like in that case, the observable was just the coordinates of the point. I wasn't really calculating any function on top of that, but I am here. I'm yes, my raw variables are. We can look at what they are. I've just got three. I've just got the lightest neutrino mass, and these two mixing phases with the other two neutrino masses, and I'm assuming that the mass scale is fixed. Not the scale, but the relative masses. I'm taking those values from what we think we know them to be. So let's see, delta squared M12. These are the squared neutrino mass differences, 3 and 4. That's these numbers for the normal case, and these for the inverse case. Now, I also know what the error bounds on these are, so if I want to be a little more fancy, I can run this distribution with those being distributed too. So rather than just assuming that parameter has one value, then every time it tries to sample from the distribution, it'll also sample from that distribution, which is just a simple normal distribution with these as the mean and these as the deviation, is the variance, I guess, and then slightly different numbers for the inverse ordering, but the important thing is that the order itself is different. Then the other sort of numbers that factor in here are called the nuclear matrix elements. So these describe, for the nucleus itself, that the experiments are built upon, which there's a lot of different ones. Another thing they argued about at that conference was, which of these isotopes is the best one for studying the neutrinoless double beta decay. A lot of people are talking about germanium right now, and also I heard a lot about molybdenum going around and xenon. And I'm not an experimentalist, but I gather that just some of these are gaseous and some of them are solid, so there's different conditions of how do you actually build the detector, what's the best way to get the signals off of these. Some of them are cheaper than others, some of them are more stable than others, so you're less likely to get decays. I think some of them are easier to model, like with nuclear physics, than the others, so we can get a better hold on the nuclear side of the process. And that's what these nuclear matrix elements capture, because we don't, our nuclear physics knowledge is not perfect either. You're solving an n-body problem where n is the number of nucleons. So, for the smallest of these, 76, that's a computationally really hard problem to do. And so the nuclear matrix element, which captures what the nucleus itself contributes to the likelihood of this decay, those are not well known. I mean, they're pretty well known, but a lot of people do different calculations, and maybe I have a plot here somewhere, and get very different answers. And I don't know. I guess the title of my thesis is something to do with calculating those better, but I haven't yet. So we'll see how that goes. But I don't see a plot of it. I should be able to find a plot. Yeah, that's the one. This picture is kind of funny. Why can't I zoom in more? Yeah, so these are these are for different nuclei, and each color is a different method of calculating the nuclear matrix elements. And I mean, no one could look at this and say that they're agreeing with each other. I mean, they're within the same order of magnitude, but there is not much consistency here, and it could, maybe the bottom people are right, maybe the top people are right, and it is a problem because it it impacts the what we expect from these experiments, how we validate the theory in a very real way. So hopefully I can improve this, or somebody else will, because it's definitely a problem. But the other thing is that these nuclear matrix elements, treating them as distributions, because these are the elements themselves, and these are the errors in the elements, some of which are quite large compared to the actual element. Did I type that one wrong? Ooh, I think we just caught a typo. That's exciting. Not checking that. Nuclear matrix elements, where are you? Okay. 038. Okay, no, that's what it says. I'm just bothered because how can it be 038 and how could the variance be so much bigger than that? Because they definitely have to be positive. Maybe my professor had a typo. Maybe I shouldn't be saying that on air. Thank you for providing the source. That was helpful. Alright. No, there it is, 038. Okay. That must be just a really skewed distribution. Yeah, I should download this paper because I definitely need to know more about how they're calculated. Yeah, that's going in the pile. Yeah, so the thing is, because these methods of calculation are similar to each other in some ways, so you're not talking like these distributions of different values for the NMEs for each isotope are correlated with each other. They're not independent, and this matrix gives all the pairwise correlations. So like this one is the correlation between the second NME and the fifth one in whatever order I put them in. So selenium and cadmium. The counting from 0, by the way. But you need to know that to appropriately model if you're working with more than if you're trying to use 2 experiments with different isotopes and apply both their bounds at the same time. You have to account for that because they're not necessarily really 2 separate experiments. It's more like 1.5 experiments. There was a lot of debate about that at this conference too. Is it really useful to put all our resources into doing more than one experiment? Whether or not that's actually going to provide all that much more information. Could that money be spent in other ways? I'm not gonna present an opinion on that because I'm not very informed, but it's definitely a debate. So the other thing that had to go into the code, once I realized I have to be sampling not just from a product of Gaussian distributions here, but a general multivariate distribution that has different covariances between the variables. And the way I found to draw from such a multivariate distribution is, where is it? Where did I put that function? Really need to organize my code. Come on, multinormal draw. It's called the Cholesky decomposition algorithm. So it's a way of taking this covariance matrix, decomposing it, because covariance matrices are positive definite, which means that what does it mean? Any invertible matrix you can express as a product of a lower triangular matrix and upper triangular matrix. And if you don't know about matrices, skip the next 60 seconds. Any positive definite matrix can be expressed as the product of a lower triangular and an upper triangular that happens to be the transpose of the lower triangular. So you really only need to find one decomposition. And once you have that decomposition, you can work with the you can do sort of a linear transformation to get the what am I trying to say? It tells that lower triangular matrix tells you more directly the way that you need to combine draws from all the individual variables with each other in order to capture their covariance. So the hard part of this operation is definitely performing that decomposition. Then you can draw from that distribution, and this just becomes one step in the overall probability distribution that I'm drawing from. So it draws from this NME distribution. It draws from these oscillation parameters, these phase variables we really know nothing about. So it's just uniformly drawing across their full range from minus pi to pi. It's just like a full possible phase angle. And then the lightest neutrino mass is a little tricky. You can set the bounds to the stuff that we know is physically realizable. So these, these, well, they're plotting a little higher than I was, but 10 to the minus 4 to 1 EV, roughly. I guess I was doing 5 to 1, but yeah, whatever. In that range, the question is, well, what distribution do you use to sample over that variable? You could choose it to be uniform, but that means that you're going to spend a lot more time in, like, for example, you're going to spend 10 times as many samples in the range from 10 to the minus 2 to 10 to the minus 1 as from 10 to the minus 3 to 10 to the minus 2, because those exponentials are on. The difference is a log scale. So if we want to seriously consider both this small range and this large range with kind of equal priority, what we need to do is sample according to a logarithmic distribution. I've tried it both ways, and yeah, if you do it the linear way, it spends so much time sampling up here, it takes a lot longer to resolve these features of the distribution. So sampling the log way is better in this case. And there's general lessons to be learned there about if you have the choice of what your sampling distribution is, because in the Monte Carlo Markov chain algorithm, the sampling distribution you pick literally doesn't matter with enough time. That's the caveat, is if you run it forever, no matter what distribution you picked, you will eventually get to a reflective sampling of the real underlying distribution. But we don't have infinite time. We'd like to do this efficiently and be able to do lots of runs in a short amount of time. So trying to pick a way of sampling that covers the feature space nicely is smart. So that's hopefully what I have done. It seems to work, and the rest of the stuff in here is just the means of calculating each of those neutrino functions. So the double beta decay effective mass, the single beta decay effective mass, just taking the sum of the neutrinos. More technical garbage about drawing from the distributions. The one interesting thing in here is deciding what constraints to actually put from the experiments. So the first time I ran this, I think I was just sort of copying off my professor's code. I had 3 different experimental bounds from different isotopes. These are the on-the-ground neutrinos double beta decay experiments. And then I had 1 from a single beta decay experiment, and I had 1 from the Planck cosmological bound on the sum of the neutrino masses. And my plots looked okay. I mean, I was generating points in the right range, but they were very jumpy, and they had all these weird vertical streaks. And my professor pointed out that the reason that was happening was that I was over constraining. I was putting experiments down that taken together, like I was over interpreting these experiments and bounding this, past these bands. So my algorithm is trying to sample in this space where the bands are, but it's also repeatedly being told to go somewhere else. And so the result was just kind of jumping back and forth without any purpose and not settling on the real distribution. So now it's down to just one isotope constraint and the sum of the masses. And between those two, I get some much nicer plots, which are here. Let's start with this one. So this was the first plot that I ran that actually looked half decent, where I get these two bands that, well, I got the colors backwards, don't I? But it's, where is it? It's these two. And you know, as in on the left side here. Do I have another better picture? Yeah, that's even better. I do have it backwards. I should really switch that. You know, it's roughly getting the shape. There's a lot of these outliers here, which is actually the thing that I need to fix, is kind of where are all these points coming from that I would say don't belong, don't look like they should be there. I thought maybe it needs more burn-in steps, and what that is when the algorithm starts, you don't start saving points for the final result right away, because there's a lot at the beginning that you kind of expect to be very inaccurate. It's starting somewhere out in the nether regions here, meandering its way in to the distribution, and once it gets there, it should stay there. So if you know roughly how long that takes, it has to go through that first part, but you can throw that data away. It's not useful. And because of this property that if you run it forever, you eventually get the right distribution. You can throw away any data you want if it's done. I mean, unless you're intentionally throwing away certain regions of data. But if you're just throwing away a certain data for a certain amount of time of the run, that's not going to impact your final result, except to maybe speed up the convergence time. So I thought maybe I wasn't putting enough burn-in steps in, and I think I went from 10,000 to 100,000. And it looks a little better, but there's definitely still these outliers. I mean, the distribution's fuller, which to me is a good thing. That means it's spending more time where it's supposed to be. But what I need to work on next is figuring out what's going on with these. It may be they're supposed to be there. I need to plot the actual analytical bounds, because there are some hard boundary curves here and here on what these values can take. Like, forgetting about any experiments. These are just based on the equations that relate these different variables together. There's certain hard limits, and I think there's a limit down here, and if it's going past that, then something's wrong. But overall, on the bright side, this looks right. This looks roughly correct, so I'm pretty happy about that. And then I also have plotting against the sum of the masses, which should match that right side plot, but it doesn't. That's interesting. I'm not sure that right side plot is actually correct. I'm pretty sure I've seen something different than that. This is all called the lobster plot, by the way. Yeah, that's plotting against sigma. That's much more like what I have. So I'm gonna go ahead and believe that's right. I don't know what's going on in the other paper, but that's what it's supposed to be qualitatively. Again, there's some outliers down here. I need to figure out what's going on there. So that's kind of the progress so far. What else did I learn how to do? I learned how to run Python code from C, which was kind of fun. And the way I did that was I wrote this Python script, which is just for the plotting. So I have writing all this data into .dat files, like column spaced, and I wanted it to plot automatically with certain labels and certain. I would make sure it's a log plot and certain axis bounds, just so I don't want to have to do that every time. But I wanted to be able to specify and see which variables I want to plot each time, and also what the labels should be, so it can just be as automatic as possible. And if someone knows a more efficient way to do this, please let me know. But the way I'm doing it right now is having this Python script, and you can run Python scripts directly from the command line in Linux and Bash with just like a Python execute this command kind of command. And so I have C in my C here going to the terminal and running that Python command, and just in text passing in the names of the variables that it's supposed to plot and the labels and the file name. So that's how I'm doing it right now, which works. I don't know if that's the best way, but it's not a bad way. Yeah, so sort of my two goals. I'm going to work on this for the rest of the night. Figure out where those outliers are coming from. Okay, 3 goals. Figure out where the outliers are coming from, if they are, which means, second goal, plot these analytical bounds as curves and see where the data fits in with there. And then third, make this faster. It's pretty fast right now. It's definitely faster than the Mathematica code, but it could be faster than it is. Like, I don't know, how long does it actually take? If I do, let's do 10,000 burn-in steps and 10,000. I'm going to change these bounds actually, just so I'm more accurately matching these plots. Let's do 10,000 and 100,000. Why not? I'll save more of them. What should I call this? Faster. I mean, it does, it does groove. It does roll along there. Well, how's that going? What else can I talk about? Okay, there we go. Yeah, sometimes it does this. Sometimes it gets really stuck up in this higher range, and I don't know what to do about that. But anyway, yeah, that's not important right now. The question was, how fast was that? 85 seconds. I think it could be faster, and I think what I need to do is figure out exactly where it is being slow. I mean, there's a lot of steps that go into this, and like some of these have to be very quick. Just computing the physical observables from the raw data, that has to be super fast, because it's just multiplication pretty much. But I think drawing from some of these distributions, that might be pretty slow. Some of the matrix operations probably pretty slow. Because that was the other fun thing I did. Was I wrote a matrix library, which I will put on GitHub and make available if anyone wants it, from scratch. Just a matrix library for C++, which, I mean, I'm still adding features to it, but you can do all the basic stuff. You can make matrices of any side, multiply them with each other, multiply them with vectors. Do this decomposition. I'm going to add, basic inverting and eigenvalue sorts of algorithms, but it's pretty fast for what it is. I could probably find some ways to make it faster, but it was a fun challenge doing this from scratch and figuring out how to store that data. And ultimately my goal, which isn't a popular view that I'm about to express here, but I really like MATLAB. I think MATLAB's good. I think it's a good thing. And so I've tried to make the syntax of my matrix library as close to MATLAB as humanly possible in C. So for example, in this, where's the multi-normal draw? Yeah, this is a vector, means I'm just adding it to a matrix times a vector. You can do that. You can't usually do that in C, so be impressed. Yeah, I'm pretty happy about that. This actually should be the cover photo for today's stream, because it's definitely the most exciting thing I've done. Alright. I guess I talked for a lot longer than I was planning to, but that kind of completes the talking part for today. I'm just going to work on stuff for the rest of the time now. If you want to stay on board, that's cool. Feel free to ask questions. But I think my goal is to I think the first thing I want to do is just try to plot these boundary lines and figure out what's going on there, and then I'll worry about the sampling stuff after that. Here we go. I guess I only need to calculate these once, and then I'm kind of done. Yeah, I can just save these in like a data file once I've calculated them once and plot them every time in Python. That's definitely the way I should do it. Okay, I think I see what's going on here. To produce these sorts of ranged plots, it seems like what we want to do is I'll let my plot again. Yeah, so on these plots, what I want to do is for each of these points, for every, say, latest neutrino mass value, the maximum bound is pretty easy to find. Apparently, it's just independent of those phases I mentioned. I can just sort of express it as a sum where both of those phases are set to 0, and I'll get these two nice upper curves. So that's easy, but I'm pretty sure it's working on that end. It's the lower ones where I'm having problems, and it looks like that to calculate those, I have to try setting the phases to a bunch of different combinations and taking whatever the least one is. That's how my professor did it anyway. And that should give me a lower bound. And do that all the way across, so I'll get some sort of bands. That seems achievable. I don't think I want to do it tonight, though. I think I'll do that tomorrow, but at least I know how to do that now. What I do want to do tonight is find out what's slow. So, how do I set a timer? This really good Italian bakery near Euston Station. We've got these, it's like an arancini but with cannoli filling in it. It's very good. Oh. Tastes like carnival food, but I need the calories. That's okay. Cool. I'm measuring time now, and it's pretty efficient. I mean, I have no frame of reference, but it's something. So 500 microseconds per step of the algorithm. Is that good? I don't know if that's good. Let's make it better. How to make your code really ugly is put in time step measurements around every single line, but it must be done. That seems like enough. Ooh. Oh. Interesting. That is the opposite of what I expected. Okay, so drawing the new state is actually barely taking any time at all. Evaluating the distribution is taking time at all. And where's the rest coming from? Because those numbers don't actually add up that close. Oh, this thing. Well, it can't be taking division. That's literally one step. I guess. I mean, there's the function calls, I guess. That could do it, but. Alright, I'll check this part. This is so interesting. Oh, exception is not a word, but it should be. Yeah, almost all of it is coming from evaluating the distribution. That's really, really interesting. Distro candidate, prior candidate. Okay. Oh, what am I? Oh, okay. Wait, maybe that doesn't make sense. Draw. Okay, no, that does make sense, I guess, because it's pulling from a couple different distributions that are not nice. I just want to know which ones are slow, I guess, at this point. So, these distribution functions are just really bad. That's what I choose to believe. Okay, it's not the distributions. It is objectively... Wow, the function calls are taking a lot of time. I wonder if that means that my class is bad. That's possible. But for sure the biggest chunk of the time is drawing these observables. So how do I fix that? How can I make that better? together, because I suspect they're pretty fast as it is. I could be wrong. Oh, that's pretty distinct. It's definitely drawing from multivariate distributions, and that's taking up like half of the total time at least. So that would be good to get rid of somehow. Alright, I think I'm going to pause there. Thank you for tuning in, and see you next week.